This is ELC131, Circuit Analysis 1, and this presentation is on resonance. Now, the frequency where X sub L and X sub C are equal is defined as being the resonant frequency, symbolized with F sub R. And mathematically, X sub L equals 2 pi FL, X sub C equals 1 over 2 pi FC. And figure 1 shows us the plots of X sub C and X sub L as a function of frequency. And these two functions, X sub L and X sub C, must intersect at some point. And referring to figure 1, where these two plots intersect is the resonant frequency. So at resonance, if X sub L and X sub C are equal, then I can express this as 2 pi times F sub R times L equals 1 over 2 pi F sub R times C. And I rearrange the equation to yield F sub R squared equals 1 over 2 pi squared times LC. So the resonant frequency mathematically equals 1 over 2 pi times the square root of LC. Now, let's look at a series RL circuit at resonance. Figure 2 shows us the impedance vector diagram for a series RLC circuit. And we recall that mathematically impedance equals the square root of R squared plus X sub L minus X sub C squared. And if at resonance X sub L and X sub C are equal, then we yield that at resonance the impedance of the circuit equals R. The terms X sub L and X sub C canceling, giving us that Z equals the square root of R squared. And in figure 3, we see the voltage vector diagram for a series RLC circuit. And again, recall from our previous discussions that Vs equals the square root of VR squared plus VL minus VC squared. And if at resonance X sub L equals X sub C, then VL has to equal VC. Therefore, at resonance, the resistor voltage equals the source voltage. Again, V source equals the square root of VR squared plus VL minus VC squared. And if VL and VC are equal, then V source equals the square root of VR squared. And we can also say that at resonance, the current in the circuit is equal to V source divided by R, because of course the total impedance of the circuit is equal to R. So let's look at the analysis of a series RLC circuit at resonance. For the circuit of figure 1, we have a source voltage of 14.14 volts peak, and the frequency of the source is not given because this AC source spans a wide range of frequencies, such as that would be seen in an audio amplifier. And this source is connected to the series combination of a 100 millihenry inductor, a 1 microfarad capacitor, and a 100 ohm resistor. So the resonant frequency for the circuit, again, is 1 over 2 pi times the square root of LC. For the circuit of figure 4, the resonant frequency is 503 hertz. Now, at the resonant frequency, the inductive reactance is 2 pi FL, which equals 316 ohms. And at the resonant frequency, the capacitive reactance is 1 over 2 pi FC, which also equals 316 ohms. So at resonance, the impedance equals the square root of x sub L minus x sub C squared plus R squared, which equals 100 ohms. Now, referring to the vector diagram for impedance shown in figure 5, we see that at resonance, the impedance equals R, which equals 100 ohms. Now, at frequencies above the resonant frequency, x sub L now becomes greater than x sub C, and the phase angle moves into the first quadrant because, of course, the vector sum of R plus x sub L plus x sub C will be greater than R because x sub L is greater than x sub C. And likewise, at frequencies below the resonant frequency, the impedance increases above 100 ohms because now we're operating in the fourth quadrant with x sub C being greater than x sub L. Now, figure 6 provides us a plot of the impedance as a function of frequency. And note that with this plot, we see that impedance is minimum at the resonant frequency, 504 hertz, and impedance increases below the resonant frequency and above the resonant frequency, again because we're now operating at frequencies where either x sub C is greater than x sub L or x sub L is greater than x sub C. Now I want to point out too, looking at the plot in figure 6, that the x-axis is plotted on a logarithmic scale, and this is done to provide a more symmetrical graph of impedance as a function of frequency. We'll talk more about logarithmic scales when we start looking at the response of filter circuits. Now we look at the voltages and the current and voltage in a series RLC circuit. And of course, at resonance, the current in the circuit of figure 4 is V source divided by R. 10 volts divided by 100 ohms equals 100 milliamps. And again, these are RMS quantities for voltage and current. And figure 7 provides us with a plot of current as a function of frequency for the circuit of figure 4. And again, note that current is maximum at the resonant frequency. At frequencies below and above resonance, the current in the circuit will decrease because, of course, impedance increases. So at the resonant frequency, we can calculate the inductor voltage and the capacitor voltage, which equal I times x sub L, which equals I times x sub C, and we yield a value of 31.6 volts. And I want to point out this is important because note that VL and VC are much greater than V source, which is 10 volts. It's not uncommon in these series RLC circuits to have voltages dropped across the inductive and capacitive components that are greater than the source voltage. And again, it's because these two voltages cancel that this situation can occur. Now, let's talk about parallel RLC circuits at resonance. Again, if at resonance x sub L equals x sub C, then IC and IL have to be equal. And we recall from our discussion of parallel RLC circuits that the source current is the vector sum of IR, IC, and IL. Mathematically, I source equals the square root of IR squared plus IC minus IL squared. So at resonance, if x sub L and x sub C are equal, IL and IC are equal, then the then the IC and IL terms will cancel, giving us that I source equals the square root of IR squared, or I source equals IR. And the admittance of this parallel circuit, again, the total admittance equals the vector sum of capacitive susceptance and inductive susceptance and conductance. So mathematically, y equals the square root of b sub c minus b sub l squared plus g squared. And of course, at resonance, if x sub l and x sub c are equal, then b sub c and b sub l are equal, leaving us with y equals the square root of g squared, or y equals g. And at resonance, if y equals g, then impedance equals R. So we look at figure 9, and this shows us or gives us a parallel RLC circuit. Now actually, this is a series parallel RLC circuit. And looking at the circuit in figure 9, note the addition of the resistor RS, the source resistor. Now this source resistor has to be included in the circuit because at extremely low frequencies the inductor is nearly 0 ohms, and at extremely high frequencies the capacitor is nearly 0 ohms. So if we did not have our source in the circuit at low frequencies and high frequencies, this would put a short across the source voltage, which of course would demand too much current from the source. So our calculation for the resonant frequency is the same as always, that the resonant frequency equals 1 over 2 pi times the square root of LC. For the circuit of figure 9, again, the resonant frequency is 503 hertz. Now, at resonance, again, since IC and IL are equal and opposite in direction, the only current delivered by the source flows through RS and R1. So the source current at resonance will be 10 volts divided by 100 ohms, or 100 milliamps. Again, the 10 volts and the 100 milliamps are RMS quantities. And the vector diagram for the circuit of the parallel RLC circuit is shown in figure 9. And again, note at resonance, the resistive current and the source current are equal at 100 milliamps. However, at frequencies above resonance, now we've got more capacitive current than inductive current, and the source current will be in the first quadrant. At frequencies below resonance, the inductive current will be greater than the capacitive current, and I source will be in the fourth quadrant. I note an error here. It should say that when IS is greater than IR at frequencies below resonance in the fourth quadrant. Now again, at resonance, IL equals IC, which equals VR1 over X sub L and VR1 over X sub C. For the circuit of figure 8, we had that the voltage across the resistor R1 was 9 volts. 9 volts divided by 316 ohms gives us 28.4 milliamps. So referring to the plot in figure 10, which shows us source current as a function of frequency, that current is minimum at the resonant frequency. However, the source current will increase at frequencies below resonance, and the source current will increase at frequencies above resonance. Again, this is because at frequencies below resonance, we now have current flowing through the inductor, so I source increases, and at frequencies above resonance, we'll have current flowing through the capacitor, and I source will increase. Again, note that in the plot of figure 10, the x-axis is plotted on a logarithmic scale, and this is done to provide a more symmetrical curve for the source current. So again, at resonance, X sub L equals X sub C. In a series circuit, VL equals VC. Those two voltages cancel, and VR equals the source voltage. In a parallel circuit, at resonance, again, X sub L equals X sub C, IL equals IC, and these currents are opposite to one another. So at resonance, the source current equals the resistive current.